Yeah, so first, thank you very much to the organizers. I'm really, really sorry not to be able to be there. I was very much looking forward to it. But since, I mean, as you may know, I got COVID, probably it's best for all of you if I stayed at home. Nonetheless, I hope there's going to be time and occasion for discussions in the near future. So what I want to talk about today is a joint project with Martin Heirer, and time allowing, I'll also at least mention a project that we have together with Martin and Rongfeng Sun. And even though the motivation and the topic, so this Brownian Castle, which is a stochastic process, comes from quite far away from the topic of the conference, actually the construction of the process itself is very close to many of the things which has been seen, and I think that a lot of interesting connections can be drawn. So let me start with the motivation. So the motivation comes from the context of random interface in 1+1 dimensions. So a random interface is nothing but an interface H from R times, let's say, R plus into R, which evolves in time and whose evolution is driven by a stochastic forcing. Now, in this context, two universality classes have generally been considered. So the first was introduced in the mid-80s, or at least not the first, but the most famous was introduced in the mid-80s by three physicists, Kardar-Parisi-Zhang. And it owes its importance to the fact that it contains a wide variety of systems which may look very different from one another. So for example, there are stochastic partial differential equations, and in particular the KPZ equation. This second picture instead is taken from a physicist paper by Takeuchi and Sano. And the reason why I included it here is because what you see is that, so the interface we are looking at is this, and the different colors represent the time evolution of this interface, okay? So in this case, what the physicists did was simply hit with a beam epitaxy a liquid crystal, and they looked at the evolution of the crystal, so the evolution of the interface. And at last, well, the last example is the asymmetric simple exclusion process. Here we have particles that simply perform independent random walks, but they cannot jump to positions which are already occupied by another particle. And here the interface, so this asymmetric simple exclusion process can be mapped to a random interface, and this is nothing but the corner growth model that we see above. And the asymmetry here lies in the fact that somehow the particle prefers to jump to the left than to the right. The second universality class is instead the Edwards-Wilkinson universality class. In this case, so an example of a model belonging to it is the symmetric simple exclusion process. So the dynamics is the same as before, but this time the particles perform independent random walks, which have the same rate of jumping left or right, okay? Now, we know quite a lot about these universality classes. So first, the scaling exponents. So what do I mean? What I mean is the following. So take your microscopic model, imagine that for some reason you suspect it belongs to either the KPZ or the Edwards-Wilkinson universality class. And then the question is, what is the scale at which I need to look in order to see non-trivial fluctuations? Well, in the case of KPZ, these scaling exponents are 1, 2, 3, while in the case of Edwards-Wilkinson, they are 1, 2, 4. And which means that if I look at fluctuations of order epsilon, then I need to look at a spatial distance of order epsilon to the -1, and I need to look, epsilon to the -2, and then I need to look at a time of order, I need to wait for a time of order epsilon to the -3 in the case of KPZ and 4 in the case of Edwards-Wilkinson. And when I subtract a suitable mean, then this object should converge to a non-trivial limit. And we know also more. So meaning we know the one-point distribution of this non-trivial limit in both cases. We know what is the limit process. So if I look at this as a space-time function, we know what's its distribution, or at least we have a way to characterize its law. And in one case, this is the famous KPZ fixed point, which has been recently characterized. In the case of the Edwards-Wilkinson universality class, the object is Gaussian and is simply given by the solution of the stochastic heat equation, which here psi is a space-time white noise. And so these are the three things that you really want to know about these universality classes. So scaling exponents, one-point distribution for the limit point, and a characterization of the limit process, okay? And then clearly you want to show that there is a family of models that indeed belongs to these universality classes. But in this context, we even know more. So meaning we know what's the connection between these two universality classes. So we know somehow how the transition from the Edwards-Wilkinson to the KPZ universality class happens. And this transition is encoded by a crossover process, which is the so-called KPZ equation. It's this equation here. And what does it mean to be a crossover process? I'll say it very vaguely, and I just wanted to add it because maybe time allowing, I'll show you something in this, like similar to this, which plays a similar role later. And so it means that the solution of the KPZ equation, this is a very nice Markov it's a nice Markov process. And if you look at small scales, so if you zoom in, then what you see are Gaussian fluctuations. So at small scales, the solution of the KPZ equation behaves as the Edwards-Wilkinson fixed point. But instead, if I look at large scales, so if I zoom out under the 1, 2, 3 scaling, then what I see in the limit is the KPZ fixed point. So the KPZ equation, in this sense, interpolates between the Gaussian Edwards-Wilkinson behavior and the KPZ behavior. Okay, so our investigation started sort of with this picture in mind. And the model we were looking at, which should belong to one of these universality classes, is the ballistic deposition. Now, the ballistic deposition is a very simple model to describe. So imagine that at every spatial location, you have a Poisson clock. And when the Poisson clock rings at location X, then the height function is updated and takes the value of the maximum between the value of the height function on the left, on the right, or the value it had before plus 1. Okay? So let me show you this. So for example, imagine this is my interface. This is my location X. Then if the Poisson clock rings at this location, then my height function is going to take this new value. If instead it rings, let's say, at location Y or X plus 1, so here, then it's simply going to take this value here, okay? So essentially the block falls and sticks to the first point it touches, okay? So the dynamics to explain is very simple. And if you try to, and you can even think of this as sort of the easy version of Tetris, okay? So in which you only have blocks which are cubic, which are small squares, and they don't have very fancy forms, but they stick to the first point they touch. Now, if you run a simulation, this is what you end up seeing. And again, here the different colors represent the time evolution of my interface. So what you can tell, for example, is that okay, so the surface here is quite regular. And if indeed it belongs to the KPZ universality class as it's conjectured, then this surface should essentially be a Brownian motion for any fixed time. But in the time evolution, you also see these big holes, which are piling up. And this is sort of reminiscent of the slope. So, I mean, this is a consequence of the slope dependence in these type of models. Now, despite the simplicity of the description, there is really little which is rigorously known on ballistic deposition. So there are a bunch of simulations that seem to suggest what we just said. So the ballistic deposition should belong to the KPZ universality class. But apart from that, apart of numerical simulation, rigorously, there is almost nothing. So the only thing we know is, for example, that if we look for a law of large numbers, so a hydrodynamic limit, well, this hydrodynamic limit exists, and this can be deduced by subadditivity argument, and it's a result by Sepalainen in early 2000. But you don't even have an explicit expression for the PDE, which should describe this hydrodynamic limit. Okay, so very little is known. So what we wanted to do is to come up with a modification of ballistic deposition, which encoded its main features, so that somehow the behavior should be the same, but which could be tractable. And so the way in which we modified the model is the following. So this, again, is the dynamics. Then we introduced a parameter, a beta, which can be thought of as an inverse temperature. And instead of the dynamics being given simply by saying that h takes the value of the maximum between these three values, what we imposed is that, okay, so let's again, we have Poisson clocks at each spatial location. And if the Poisson clock rings at location X, then the height function takes one of these values according to a certain rate, which depends on beta and on the height function itself. And how do we pick these rates? Well, we pick them in this way, so in the way which is written here, but we want to pick them in such a way that the maximum is favored, so that somehow the same type of behavior should be observed for beta ballistic deposition, for beta positive, and for ballistic deposition in general. And notice indeed that this is the case. So if if h at x plus 1 is the maximum among the three, then the rate at which my height function is going to take this value is higher than in the other cases. So it's more likely, my height function is more likely to take the value to the right. And so what do we expect in the limit? Well, if I simply take brutally beta equal to plus infinity, then this reduces to the classical ballistic deposition. And so according to the conjectures which are lying around, this should belong to the KPZ universality class. Now for beta strictly positive again, so the behavior and sort of the main features of the model are unaltered. So what one would expect is again to see KPZ type behavior. But what happens for beta equal to 0? Now, for beta equal to 0, these three rates are equal, and they are independent of the height function. And now notice that, so what can happen is imagine you have, so this is your height function, and you have now, and the clock, the Poisson clock rings at location x, then what may happen is that my height function sort of decides to take the value on the right, so this value here, so that the new height function is going to be something like this. So in particular, so while in the case of ballistic deposition, we had a preferred direction, so somehow our surface was growing, in this case, well, we are sort of breaking it in the sense that now my height function is allowed also to take values smaller than the value it had before. Now, if we believe in the previous slide, on the 2 slides ago, so in which I said, okay, there are these 2 universality classes, then in principle, what we should see for beta equal to 0 is, I mean, if we believe that for beta strictly positive, we have KPZ, for beta equal to 0, since we are sort of breaking one of the symmetries or the asymmetries, maybe we see Edwards-Wilkinson. Now, I want to show you a simulation of the process, and this simulation, okay, the rendering of the simulation is suboptimal when I share the screen. Would have been better for me to be there, but okay, so anyway, I'll show it to you.
Maybe a quick question before of the simulation, like is there a way to describe these processes via particle system that then lead to these height functions, or
well, yes, but it would be a very complicated particle system. So both, even if you take simply ballistic deposition, there is not a particle representation which is obvious. What you would need to do are sort of 2 types of particle in your system which interact in a non-trivial way. But somehow it's really not obvious.
Okay, so maybe not even so useful then.
I mean, it could be. Anything you can prove about the ballistic deposition would be quite an achievement, especially if one doesn't use these sort of monotonicity property or ergodicity properties, sorry, subadditivity properties. But okay, yeah. But so far, yeah, no, it's not clear.
I see.
But I'll give you, yeah.
And also regarding, I don't know, some stochastic duality properties, nothing is known for these models, or?
No, nothing. Even for ballistic deposition, it's not clear what's the duality. I mean, clearly, okay, you obtain exactly the same process if you simply run the time backwards. Okay, you simply, this would simply switch the maximum to a minimum, but you wouldn't get much. So you would want some duality which sort of can tell you more about the process itself. But no, so far nothing is known.
Okay, thank you very much.
Any other question?
Sorry?
Any other question?
Any other questions? No, it seems no other questions. Thank you.
Okay. So then I'll show you a simulation. This simulation was done by Martin Heirer. I'm not so good at programming, and actually, it even allows you to see scale. I don't know. It's very okay. Anyway, so this is at the beginning, and then I'm rescaling, and I want to show you. And this is what you see at large scales for ballistic deposition, for a zero ballistic deposition. So the case in which we take beta equal to 0. Now, let me pause for a second. So notice first that if you remember the picture I gave you before, in that picture for ballistic deposition, what you saw was something which was, a surface which was quite regular. While here, we see macroscopic discontinuities. These discontinuities survive for a certain amount of time and then they vanish. Okay, and this discontinuity simply oscillates and then at some point vanish. In the case of ballistic deposition, there was none. And let me also say that for the Edwards-Wilkinson, so the solution of the stochastic heat equation, this is, well, if you fix a time, this is nothing but a Brownian motion, so which in particular is continuous. In other words, this simulation suggests strongly that this process, so that the scaling limit of zero ballistic deposition, is neither in the KPZ nor in the Edwards-Wilkinson universality class. Let me also show you what happens if I take beta positive, but very small. So for example, 0.1. And now you see what you see is an immediate regularization. So here it again really looks like the same behavior we saw for ballistic deposition. Okay, sort of even for beta very small, you immediately see a regularization. Okay, and now I'll go back to the presentation. Okay, so what's the goal of this talk? Well, the goal of this talk is to construct the scaling limit of the zero ballistic deposition. Okay, and how this process is new to our knowledge, and we called it the Brownian Castle. Well, okay, because it's sort of reminiscent of a castle. You can think of, the life of a castle through history, very fast forward. And okay, so you have these turrets, and moreover, we are in the UK, so they are very proud of their castles. So anyway, so what I want to do is to, on the one hand, provide a global construction of the scaling limit of the zero ballistic deposition, prove some of its pathwise properties, and at least state the convergence and show that the zero ballistic deposition indeed converges to it. So that in particular, the Brownian Castle is indeed a universal object, which has its own universality class. Okay, but to do so, it's better to take a step back and look at the discrete system. So in particular, look at the zero ballistic deposition and try to understand its definition. Because it's from there that we're going to start seeing which are the connections with the topics which have been, and with the talks which has been given before me. Okay, so what's the dynamics? Again, we have independent Poisson clocks at every spatial position. And then when the Poisson clock rings at position X, then my height function with the same probability can take the value on the left, the value on the right, or the value it had before plus 1. Now, each of these three steps happens with the same probability. Okay, so in particular, we can think of the zero ballistic deposition as being driven by three independent Poisson processes, Poisson random measures, with the same intensity. Okay, and since this probability is independent of the height function, of the specific value of the height function, well, we can represent it. We can use Harry's graphical representation in order to give a different interpretation or different formulation of the zero ballistic deposition. And how do we do that? Well, we consider our space, our discrete space, and we're going to we consider a realization of these three independent Poisson processes. And we're going to draw arrows to the left for those, so for the Poisson process that forces my height function to take the value on the right. We're going to draw arrows to the right for the Poisson process that forces my height function to take the value on the left. And at last, we're going to draw dots, so these dots, for the Poisson process that increases the value of my height function by 1. Okay? And now, what happens if I want to know the value of my height function at location y and at time t? Well, the only thing I need to do is to follow the arrows backwards until the initial condition. So look at the value of my height function at the initial time, and at location X, and then count the number of dots that we have met on the way. Okay? It's not difficult to see that this indeed gives you the value of your height function at this specific location. So notice in particular that the red line is nothing but a random walk, and these dots here are nothing but a Poisson process indexed by my random walk. And now what happens if I want to know the value at multiple points, or for example at 2 points? Well, I have to do the same thing. So I start from this point, for example, I follow the arrows backwards, I look at the value of the initial condition, and then I count the number of dots on the way that I met along the way. And so in particular, you see that what we end up with is a system of coalescing random walks, because these are all coalescing random walks. And on top of it, so we have a Poisson process, which is indexed by the trajectories of my random walks. Okay? Alternatively, one could construct the finite dimensional distributions at a given time or at different times as follows. First, I draw my system of coalescing random walks, let's say starting from this time and this time. And then I attach to each of these time intervals, I attach independent Poisson processes whose rate, or Poisson random variables, whose rate is simply given by the time span of these interval here. Okay, so this is another way to construct the finite dimensional distributions of this process. Good, but now how should I rescale the process in such a way to see a meaningful scaling limit? Well, as I saw in the previous talks, well, I need to rescale space and time diffusively because I want these random walk to converge to Brownian motion. Okay, so the relation is 1, 2 is diffusive. But then I also need to rescale the size of the fluctuations. And the size of the fluctuation are induced by the Poisson process, which is indexed by my random walk. But in particular, at a given time t, the value of conditioned on the random walk, what I see at this point is nothing but the value of a Poisson random variable with parameter t, okay? So which is simply the time length of my interval. So in particular, in order to have also the Poisson process, we need to, okay, compensate it and then rescale it. How? Again, in a diffusive manner. So in particular, the relation between the size of the fluctuations and time is the same as the relation between space and time. So in particular, the scaling exponents under which I can expect to see something meaningful is 1, 1, 2, and not 1, 2, 3, and neither 1, 2, 4. So in particular, really, so this is a completely different universality class. I mean, if the simulation before didn't convince you, maybe these arguments is more convincing. And what do we expect it to be the scaling limit? So now, as we said, so for the scaling limit, well, we expect that the random walks are going to converge to Brownian motions, in particular to coalescing Brownian motions. And then how do I describe the finite point, the finite dimensional distributions? Well, what I need to do is to attach to each of these branches here and this last branch, I need to attach Gaussian random variables, which are going to be the scaling limit of the Poisson random variables that I was attaching here and here and here and so on. So, and what is the size? What is the variance of these Gaussian random variable? Simply these lengths here. Okay. So I will need to attach to each of these branches independent Gaussian random variables whose variance is nothing but the length, the time length of this branch. In particular, if I want to know the distribution of the increments between these two, starting at these 2 points, well, what I need to know, this is going to be nothing but a Gaussian random variable with variance given by the time at which these 2 paths coalesce, or twice as much. Okay? Does this make sense? Okay, so if so, hopefully, if you have any questions, please interrupt me at any time. So in particular, but so as I said before, in the previous slide, I want to prove a theorem which gives a full and a global characterization of the Brownian Castle, which in particular forces me to be able to follow a trajectory starting from every space-time point. So in particular, what I need is sort of the full flow. I need the full Brownian web, as was discussed in the previous slides, because I want to be able to follow a trajectory starting from every space-time point so that I have a global characterization, a global definition of my of the Brownian Castle. And okay, so the Brownian web has been mentioned various times, in particular in the previous talks, but also in Sandra's talk. And okay, so this is an object that has a long history, and here what you see is another simulation still made by Martin, and the colors are chosen in such a way, sort of the paths that survive the longest have stronger colors. So that's the reason why you can sort of distinguish, for example, these red paths, because this is very long and doesn't coalesce with any other. While if a path starts here, then this is going to have a lighter color. Okay. Right. And so, but okay. So one thing about the Brownian web is that, okay, it has many different characterizations, but most of the characterizations I'm aware of are based on, so try to view the Brownian web as a family of paths, as a compact set of paths, exactly as in the talk before. But the thing is that for our purposes, since we want to build a Gaussian process on top of it, and then we also want to prove convergence, what we really need to encode is the coalescence structure. As I said before, if I want to look at, I take 2 points and I want to know what is the joint, so the joint distribution of the Brownian Castle, well, this is going to be a Gaussian random variable whose variance is nothing but the ancestral distance between 2 points on my Brownian web. Okay, so in particular, this is the quantity, this is the notion that we need to be able to highlight. This led us to give an alternative characterization of the Brownian web in terms of R trees, which I would like to briefly sketch. Let me say that characterizing the Brownian web as an R tree, we were not the first. This was also done in a work by Grevensoon and Anita Winter. But the type of topology we use is slightly different and somehow allows us to be global in time. I mean, okay, it's going to be clear in the next slides. So any questions so far? And by the way, how much time do I have left?
So it seems there are no questions from the point of view of the time, and you still have 10 minutes.
Okay, then then I'll try to go a bit. So I'll try to be a bit quicker than I wanted to. Okay, so
Even 15 minutes, let's say.
Okay, so then I'll take 2 minutes to explain this slide and then I'll move forward. So okay, the point. What is the point here? So here, what we want to do, on the one hand, we want the Brownian web in terms of paths that live on R2, because our process of the Brownian Castle is going to be indexed by R2 or R plus times R. On the other hand, we want to keep track of the coalescence times or the coalescence structure, so in particular, the ancestral distance between any points in the web. So what we do is the following. We start, so for example, in our construction, we start with a family of backward coalescing Brownian motions, which can be constructed the way you prefer. The probably easier way you do it, you start from a countable dense set of points, and then you build these Brownian motions inductively in such a way that they are coalescing, okay? And so this is what we see, for example, in R2. And now we want to take this picture and encode it abstractly in a space which needs necessarily to have a tree structure. So in particular, we introduce placeholders which keep track of what path I'm looking at and the time, and somehow keeps track of the time. In particular, this means, so this space tau infinity is going to sort of have this shape. So it's simply a long, sorry. So this point here is going to be mapped sort of to this path, and this point here is going to be another path that what we want to know is exactly that they coalesce exactly at the right time. Okay, so this is what the space-time infinity is. Then then we add a point, doesn't really matter. And then what I want to claim is that, so I want that the distance between any 2 points in my tree is simply given by the ancestral distance of these 2 paths. So somehow the distance between these 2 points is nothing but the sum of these 2 lengths, these 2 times interval. Okay, so I built this abstract object, and then I want to embed it back into R2. So in particular, we introduce a map, which, okay, this is missing, which is the so-called, we call it the evaluation map, that essentially assigns, so M, this is our map M, that takes a point here and assigns to it the corresponding point in R2. Okay, so we have this abstract object tau, which is a random R3, and which is simply encodes the reciprocal ancestral distance of any 2 paths or any 2 points on the trajectories of my web, and then we embed it in such a way that we see the actual web. So in particular, we end up with a quadruplet in which one element is t, one is this point in the tree. We have the ancestral distance and the evaluation. And what we can prove is that indeed this quadruplet forms this triplet is a locally compact R3, and that the evaluation map is locally holdocontinuous. And once we have these properties, and remember that here we were starting from a countable dense set of points, so what we can do is we can take the completion of this space and we can extend it, we can extend our evaluation map M. And so this is exactly the object we obtain. Now, right, so one word concerning the topology. So only one. So because these in the 2 days ago we saw the Gromov weak topology or the Gromov-Hausdorff weak topology, bug topology were mentioned. Here we take, so our topology is a Gromov-Hausdorff topology plus some conditions on the map M, a continuity, and then a Hölder continuity assumption on the map M. Sort of this topology is stronger. And the reason why we need to take this is because we don't have a measured, or there is not a natural probability or finite measure on our tree. So the measure which is going to be important for us is the length measure, which is everything but locally finite. Okay. So, and what does this topology do? Well, this first part of the topology essentially compares 2 different trees. And how does it do that? Well, it imposes that, for example, imagine so that this black is one tree, and then this red is another tree. And then it says that these 2 trees are close if the distance of these 2 points, for example, and these 2 points are similar. So somehow 2 trees are close if the coalescence times are more or less the same. While this second part requires that essentially this can be thought of as a bound on the subnorm distance between these 2 paths. So essentially what we want to prevent from happening is to have something like, imagine, okay, so this is a different picture. So imagine you have something like this, and that something like this, which are sort of close, but the coalescence time is very far away in the sort of very deep in the past. So these 2 paths, like the subnorm between these paths and these paths is still close, but the coalescence time is not. And we want to prevent that from happening. Okay, so let me, what the object we built is well defined. In particular, it has the properties we expect it to have. So meaning there is a Brownian path we can follow starting from every point, and the object we build is independent of the choice of the countable dense set we started from. Okay, and we call this object the Brownian Web tree, which actually shares many properties with the original Brownian Web. Okay. Good. So this is the first part. So what we wanted was sort of a Brownian web for which we could keep track of the relative distances between points. And why was that important? Because the Brownian castle, if you remember, had, yes, the Brownian web, but on top of it, we also need to define a Gaussian process, which needs to have a very specific covariance structure. And the second proposition shows that indeed such a Gaussian process exists, and it actually admits a Hilde continuous modification. So it's a Gaussian process that indeed does what we wanted it to do. So meaning that if I take 2 points, then this Gaussian process is sort of a Brownian motion indexed by my tree and has the right covariance structure, in the sense that if I look at the variance of the increment, this is nothing but the distance, the tree distance, the ancestral distance between these 2 points. Good. So far, what do we have? Well, we have our abstract space T, which is our tree. We can embed this tree into R2. And moreover, on this abstract tree, we built a Gaussian process, or Gaussian process B. Okay. Now, the only thing we need is essentially a way to go directly from R2 to R, which is because this is the way, this is our process, our Brownian castle is a process indexed by R2. And in particular, this requires to be able to essentially invert our map M, the problem being that if this map is clearly surjective, it has no chances to be injective. So, but this is this can be cured, and it's cured by this sort of tree map. So imagine that there are multiple points, so that in the pre-image of a given point in R2, there are multiple points. The saving grace is that these points can sort of be ordered. So imagine you have 2, and since we want at the end to be able to describe our Brownian castle as a Cadillac path, then we're going to take then we're going to associate to the point Z the rightmost point, so the point corresponding to the rightmost trajectory. Okay, and with this tour de force, we're done. So this is the expression we have, and which gives a global construction of the Brownian castle, meaning imagine that we are given the Brownian web tree, we are given a Gaussian process indexed by it, then we can define the Brownian castle in the following way. So now, this expression is actually, might seem weird, but it's easy to read in a sense. So what we do is what we said before. So we start from the point Z, then we follow our path backward up to time 0. This is our point Y. I look at the initial condition at Y, and then I need to add this term, which is nothing but the amount of Gaussian process then we pick when we move along this line. If you want, so an alternative way would be to say that essentially we are convolving, or we are integrating in time a white noise on the flow, on the Arratia flow. Okay. And why is this characterization convenient? Well, it's convenient because we can prove a number of properties for the Brownian castle. We can say that this is indeed scale invariant under the 1-1-2 scaling. It is right continuous in time, but it doesn't have left limits. And this is a point I would like to clarify next. And it is CAD-log. So for any fixed time, it's CAD-log. And it has finite p variation for any p strictly bigger than 1. It is a time homogeneous strong Markov-Feller process, and it's also strong Feller if restricted to the torus, if you look at the periodic version. And at last, we can even say, well, if I simply let t go into plus infinity, well, this process converges to its stationary measure. And this stationary measure has Cauchy increments, but is singular with respect to the Cauchy process. Now, let me explain. So there are, I think, a few things which are believable. So for example, the scaling, the Markov property, strong Markov property, even the Feller property is not hard to see. The Cauchy increments are due to the fact that if you take the increment, imagine that you start at stationarity. So somehow you take the initial condition to be, I don't know, minus infinity. So then I mean, what is the distribution of the increment? Well, this is nothing, as we said, by a Gaussian random variable with variance given by the heating time of a Brownian motion, because this is nothing but the coalescence time of two Brownian motion, at least in law. And this is an alternative characterization of the Cauchy distribution. Okay. And at last, so right continuous and card lag. So right continuous in time and card lag in space. This is something I would want to justify. Do I have 5 minutes?
So,
No.
does the speaker has 5 minutes?
No,
Yes,
I understand that
the majority say yes, so
okay.
we have 5 minutes.
I know you're all very hungry, so okay, I'll quickly finish. Okay, this picture is irrelevant because we saw it today. So the thing is that the continuity properties of the Brownian Castle are strictly related to the special points of the Brownian Web. In particular, we saw it in the previous talk. So in the Brownian Web, there are various types of points. So this is my backward trajectory. So a point could be either of this type. Yeah, okay. And so the red line is the forward path, the black line is the backward path, okay? So another type of point is this. And so there are two paths starting at the same position and then merging after a certain amount of time. And this is, okay, and actually this point must start here. And then we also have these triple points. The reason, well, they are not going to meet all in the same point, so a reasonable picture, okay? And in this case, there are these two trajectory in the forward path, which coalesce. Now, let's look for a second at this path, at this point here. Imagine we see this point. So what does it mean? Now, on this branch, we have, so let's see especially what it means for the Brownian Castle. So on this branch, we have a Gaussian random variable, okay, whose variance is given simply by this length. On this side, we have another Gaussian random variable, and these two random variables are independent. Now, this means that if I look at the difference between the left guy, so somehow my height function at x minus, so imagine that I look at ht x minus or x plus minus ht x minus, where x minus sort of I'm looking at the limit from the left and h plus is the limit from the right, okay? So now this increment is going to have distribution, which is given by a Gaussian random variable whose variance is non-zero, is strictly positive. So in particular, it means that at this point, we're clearly going to have a discontinuity, or at least with overwhelming probability, we're going to have a discontinuity. Actually, with probability 1, if I fix the special point. Now, good. And so this is the cause of the discontinuities. And at every fixed time, we know that these type of points are at most countable. So this is the reason why we see we have a card lag type function. But now, what do these points cause? Now, notice that in this picture, so what this story was telling us is that the discontinuities of the Brownian Castle lie on top of these forward trajectories. So that essentially the skeleton of the forward Brownian web contains all the discontinuities. But in this picture, it means that here we have a discontinuity, which is evolving as a Brownian motion. Here we have another discontinuity, which again is evolving as a Brownian motion. And what happened at this point? Well, at this point, the two discontinuity coalesce, they merge. So in particular, imagine that you have this picture, something like this. Now, here I have my forward, so the discontinuity is essentially moving like this. This discontinuity is moving like this, and then they merge. So this means that my height function is going to evolve essentially, at least heuristically, in this way, right? So we're going to have like this, then we have this, and then this is going to be smaller and smaller. And at the very end, oops, and at the very end, what I would need to see is something like this. And now, this type of phenomenon, so this is what I see in the limit from the left. So okay, This is what I would see in the limit from the left. And then, right after, this line is simply going to disappear. Now, clearly, so this object is not continuous or is not CAD-log, or it doesn't, I mean, this type of convergence does not happen in any of the four topologies which we've seen before. So this doesn't, neither the M1, J1, J2, M2, none of these topologies would help you in trying to obtain a well-defined CAD-log process in time, let's say, okay? Good. Okay, this is essentially everything I wanted to say. So this is, okay, we also can prove the convergence of the zero ballistic deposition in a very strong sense. So we can prove the convergence at every time out of a countable set. And this countable set is precisely the set of times in which we see triple points. Okay. And okay, let me conclude with these two things. Okay, so first, so which are the type of models we can expect belong to the Brownian Castle universality class? Well, these should be those which have vertical fluctuations, horizontal fluctuations, and no smoothing. So the vertical fluctuations are due to the Gaussian process, which is indexed by our trajectories, while the horizontal fluctuations are those due by the Brownian Web structure, okay? And there is a family of models for which display indeed these features. One on which I'm working on together with Tommaso Rosati and Martin Heirer is this stochastic PDE, in which you should think of both eta and psi to be space-time white noises. Clearly, this object makes no sense, but the point is that this gives you the horizontal fluctuations, while this gives you the vertical fluctuations. And okay, so this is a model, but actually, so okay, unfortunately there's no time, but the other thing we're looking at together with Rongfeng Sun and Martin is these crossover processes. And for these crossover processes, actually the stochastic flow of kernels which were built by Sun, Schwartz and Scherzer play a crucial role. And they can give you somehow the way they represent, it's a whole family of processes that sort of interpolates between the Brownian Castle and the Edwards-Wilkinson universality classes. And if you want, I also have a simulation for that. But otherwise, I think I want to thank you for your attention.